Okay, today's lesson is day 11 notes, which is on continuity. Continuity has a pretty standard idea where basically we're looking at when do we have to pick up our pencil when we're drawing a graph. That's kind of a layman's explanation of continuity. There's a detailed explanation that requires a 3-step verification if something is continuous at a point. But to get an overall idea, basically what we're looking at is, can I draw a graph without picking up my pencil? It can be a smooth curve like in that first drawing. It can also be kind of jagged where we have these sharp points. But as long as I can draw the entire graph without picking up my pencil, then I have a continuous function. So to the 3 steps to determining whether or not the function is continuous at a given point, we'll call that point A. Let's just call that point A for right now. The first step is looking at the limit. So we need to know that the limit at x approaches A of that function exists. We don't necessarily need to know what it is at the moment, just that it exists. So that's step 1. Step 2 is the function at that point defined? Is there a point at A so that we get f of A? Again, not concerned necessarily with what it is at the moment, just that it is defined. And then part 3 is where we do get concerned with what they are, and we need to know that the limit of that function as x approaches A is the same as the function value. So basically what that means, let's do this point right here, is the limit, as the limit gets closer and closer to that point, do those limits get closer to the point that is actually at that point A? And that's what part 3. So if any one of those 3 things is not true, then we have a case where the limit or the function is not continuous. So for example, let's draw an example of something where it's not, where we have like a hole going through that function. And then let's just say that that's at 2, and then at 3 is where the point is. So in this case, does the limit exist? Yes, the limit exists. It goes closer and closer and closer to 2. Is the function value defined? Yes, the function value is defined up there at 3. However, is the limit and the function value the same? They are not, so therefore it is not continuous at that point, whatever that point might be. Okay, there are 2 types of discontinuities. The first type on the left is what's called a non-removable discontinuity, or a jump discontinuity. That's where we kind of have to go from one spot and kind of jump a distance to get to the next spot. Or if the second part of that example, if you have an asymptote where you would have to kind of jump over the asymptote. It's called non-removable because we cannot remove the discontinuity by putting a single point in. On the other side, on the right side, we have a hole or a removable discontinuity, and they call it a removable discontinuity because we can remove the discontinuity by simply putting a point back in. Now, we're not putting that point back in, that's just why they call it a removable discontinuity. It can either be the function can be defined, like in the second example, or not defined at that point. But either way, both of these are removable discontinuities at that point. Okay, let's take a look at an example now. In example 1, we're given a graph, and basically we're going to be looking at the discontinuities at different values of x. So let's start by, in part A, looking at 5 from the negative, 5 from the positive. That would be here. So 5 from the negative gets closer and closer and closer to 3. 5 from the positive gets closer and closer and closer to 5. So because those are not the same, the limit does not exist. And the function value is right there, which is at 3. So is this continuous? The answer is no, just by looking at it. But the reason it's not continuous is that first part. Let's go back up to the examples. We've got parts 1, 2, and 3. This first part does not work. The limit does not exist. So therefore it is not. So the limit as x approaches 5 does not exist. Is why it is not continuous. And what type of discontinuity is? Well, you can see that I kind of have to jump to get from one to the other. So that is a jump discontinuity or a non-removable discontinuity. All right, in example B, we're looking at 13, which is here. So from the left, we're getting closer and closer to 2, and from the right, we're getting closer and closer to 2. So because those are the same, that limit is 2. The function value up here is actually at 3. So is that continuous? The answer is no. And in this case, it's because the limit as x approaches 13 does not equal the function value at 13. So let's go back to our reasons. Again, number 1 is good. The limit exists. 2, the function is defined, but the limit is not the same at those points. The limit and the function value are not the same. Finally, we're looking at -7 as x approaches -7, which is this asymptote here. So from the left, it's going towards -infinity, and from the right, it's going towards -infinity. So the limit is -infinity. Function value, however, does not exist, or is not undefined, sorry. So therefore, is it continuous? Again, the answer is no, and this time because f of -7 is undefined. And what type of discontinuity is that? That is a jump discontinuity or a non-removable. I forgot to mention in part B, what type of discontinuity do we have at 13? Well, at 13 we have a whole or a removable discontinuity, because we can remove it if we just changed that point. All right, pause your video at this point. Work on example 2. All right, this is the graph we're looking at. Here are the answers. Pause your video if you need to check your work. All right, now let's take a look at a second type of example that we're going to look at, where it says discuss the continuity. Whenever it says discuss the continuity, they're looking for intervals where it's continuous. Intervals of continuity. Now, it's more often than not easier to find the points where it's discontinuous, and then just find the intervals, which would be everything else. So first thing I'm going to do is I'm going to draw a picture, draw a graph, and from this graph I can tell that there's a horizontal asymptote at 1. Sorry, I did this. There's a vertical asymptote at 1. There's a horizontal asymptote at 0, and then the graph looks something along those lines. Okay, so the only point of discontinuity we have is right there at the vertical asymptote. So therefore, there's a point of discontinuity at 1, which means it's continuous everywhere else. So we would say f of x is continuous from -infinity to 1, along with from 1 to infinity, and we're using open intervals. We're using the parentheses instead of the square brackets because we do not want to include 1. It is not continuous at 1, and that's the only point where we've removed. All right, pause your video here. Start working on examples B and C. Okay, in example B, we have a hole at -2. Therefore, that's the only point of discontinuity. So it's continuous everywhere else. And in example C, we have those two piecewise functions actually connect at the same spot. So therefore, h is continuous everywhere. All right, the last type of example that we're going to look at, example 5. This time, we're given this missing value k, and what we want to do is make it so that that function is continuous everywhere. So what is the k value that will make this continuous everywhere? So what we're looking for is really, we know that this quadratic is continuous everywhere because it's a parabola, and this guy is just a line, so we know it's continuous everywhere. So really the only point that we're concerned with is right here at 1. As long as these two graphs match up at 1, then we're good to go. So looking at this guy, if that's 7, then it connects there at 8. It's actually a closed circle, and it's a parabola. The question is, what should this line be with a slope of 1 so that it connects at that point as well? So what we're going to do is we're going to plug in a 1 into both of those equations. So 1 squared plus 7 should be equal to 1 plus k. As long as these two functions are the same, again, this is this guy, this is this guy. As long as those two are equal at that point 1, then we should be good. So in this case, we get 8 equals 1 plus k, so therefore k equals 7. And you can kind of see from here, from 7, slope up 1 over 1, we get to 8, which is exactly where it connects with the parabola. Okay, work on your homework for this section, and then check your work in the key.